In 1848, a German immigrant stood at the edge of Niagara Gorge, watching the water explode against rocks 200 feet below. Engineers had declared this crossing impossible. The span was too wide, the winds too violent, the gorge too deep for any scaffold or temporary support. John Roebling looked at that impossible gap and saw something no one else could see. He saw wire. Thousands of individual wires, each one no thicker than a pencil, spun together into cables strong enough to hold a railroad train suspended over the abyss. What happened next would transform American infrastructure forever, but it would also create one of the most dangerous jobs in industrial history. Men who climbed into wooden baskets and rode across open sky, spinning wire by hand while the wind tried to kill them. This is the story of how America built 2,000-foot suspension bridges using nothing but wire and stone. And it begins with a man who understood something most engineers had missed entirely. Wire, when twisted together, becomes exponentially stronger than the sum of its parts. John Augustus Roebling arrived in America in 1831, 25 years old, trained as a civil engineer in Berlin. He had studied under the great German philosopher Hegel, and he carried with him not just technical knowledge, but a particular way of seeing the world. He believed that human progress demanded confrontation with the impossible. His first years in America were spent farming in Saxonburg, Pennsylvania, a German immigrant community he helped establish. But farming bored him. His mind kept returning to engineering problems, and particularly the challenge of moving goods across the Allegheny Mountains. The Portage Railroad in Pennsylvania used a system of inclined planes to haul canal boats over the mountains. Stationary steam engines at the top of each incline would wind thick hemp ropes, pulling boats up one side and lowering them down the other. But the hemp ropes failed constantly. They stretched, they rotted, they snapped under load. Every failure meant delays, damage, sometimes death. Roebling watched these failures and began experimenting. In a small workshop behind his farmhouse, he started twisting iron wire together by hand. He wrapped the wires in a specific pattern, each one taking a helical path around a central core. When he tested these wire ropes against hemp, the results were extraordinary. The wire rope was lighter, it was stronger. It lasted longer, and most importantly, it behaved predictably under stress. You could calculate exactly how much load it would bear before failure. In 1841, Roebling sold his first wire rope to the Portage Railroad. Within a year, hemp ropes had been completely replaced. Within 5 years, John Roebling had established a wire rope factory in Trenton, New Jersey, manufacturing cables for mines, ferries, and construction projects across the eastern seaboard. But Roebling had bigger ambitions than selling rope. He wanted to build something no one had built before. He wanted to hang a railroad bridge from wire cables across Niagara Gorge. The engineering establishment thought he was insane. Suspension bridges existed in 1848, but they were fragile things. They swayed in wind, they oscillated under marching troops. They had collapsed catastrophically in Britain and France, killing dozens of people. No responsible engineer would put a locomotive weighing dozens of tons and traveling at speed onto a suspension bridge. But Roebling had studied these failures obsessively. He understood why they happened. The bridges that collapsed were too flexible. They had no resistance to lateral forces, no way to dampen the oscillations that built up under rhythmic loading. His solution was radical. He would build a suspension bridge with a stiffened deck, supported not just by vertical suspender cables, but by diagonal stays radiating from the towers. The deck would be enclosed in a wooden truss, essentially a hollow tube that would resist bending and twisting forces. The entire structure would be locked into tension, in every component pulling against every other component, so that the bridge became a single integrated system rather than a collection of parts, and the main cables that held everything up would be spun in place, wire by wire, using a technique Roebling had invented himself. This is where the story of engineering genius becomes a story of human labor at the edge of survival. To understand wire spinning, you need to understand what Roebling was asking men to do. First, workers had to build the towers. At Niagara, these towers rose 80 feet above the gorge rim, anchored in solid rock. The stonework alone required quarrying, shaping, and setting thousands of tons of limestone blocks, all by hand. Then came the anchorages. On each side of the gorge, workers excavated massive pits and filled them with masonry. Thick iron anchor bars, forged in local furnaces, were embedded in the stone. These anchorages had to resist the entire horizontal pull of the cables, hundreds of tons of tension trying to drag the structures into the gorge. Only after the towers and anchorages were complete could wire spinning begin. The first step was establishing a temporary connection between the towers. At Niagara, this presented an obvious problem. The gorge was 800 feet wide, and the river below was a churning nightmare of rapids and whirlpools. No boat could cross safely, no scaffold could reach. Roebling's solution was elegant and slightly absurd. He offered a prize of $5 to the first person who could fly a kite across the gorge and land the string on the opposite side. A local boy named Homan Walsh won that prize after several days of attempts. Fighting the unpredictable winds that swirled up from the water. That thin kite string was tied to a heavier cord. The cord pulled a rope, the rope pulled a wire, and eventually the wire pulled an iron cable across the gap. This first cable became the Traveler. Workers on each side attached a small wheel and a basket to the Traveler, creating a primitive aerial tramway. And this is where the real work began. Picture yourself climbing into that basket. You are 300 feet above boiling rapids, suspended from a single cable that sways and bounces with every movement. The wind hits you from below, carrying spray from the falls downstream. The basket creaks, the cable groans, and you begin to move. A worker on the opposite tower turns a winch, pulling the basket across the void. Your job is to carry wire, thousands of pounds of wire, coiled in the basket with you, paying out behind you as you travel. But you are not just a passenger, you are a spinner. As the basket moves, you must guide the wire into precisely the correct position on the growing cable. You must watch for kinks, for crossed wires, for any defect that could weaken the finished product. You must do this while the wind tries to tip you into the gorge, while rain soaks the wire and makes it slippery, while your hands cramp from cold and your eyes water from the spray. The spinning process worked like this. A continuous loop of wire ran from the anchorage on one side, over the tower, across the span, over the opposite tower, and down to the opposite anchorage, then back again. This loop was called the traveling wheel. A wooden drum at each anchorage held coils of wire, and as the traveling wheel moved back and forth across the span, it laid down wire after wire in precise parallel rows. One wire per trip. One trip could take 30 minutes in good conditions, hours in bad weather, and a single main cable required thousands of wires. At Niagara, each of the 4 main cables contained 3,640 individual wires, bound together with wrapping wire into a solid cylinder about 10 inches in diameter. Do the math. 14,560 trips across the gorge per cable pair, in baskets, in all weather. The men who did this work have mostly been forgotten. Their names do not appear in history books about the Niagara Bridge. We know they came from the surrounding farms and towns, drawn by wages that were better than agricultural labor, but not extravagant. We know some of them fell. We know none of the falls were survived. Roebling himself supervised the spinning operation, riding the basket regularly to inspect progress. He was not the kind of engineer who drew plans in an office and left the dangerous work to others. He climbed the towers, he walked the catwalks, he handled the wire. The catwalks were another horror. Before the main cables were complete, temporary walkways had to be strung between the towers to give workers access to the spinning apparatus. These catwalks were nothing but wooden planks, 18 inches wide, suspended from light cables and open on both sides. 300 feet below, the river thundered. Above, the sky wheeled with clouds, and you walked that plank, carrying tools, carrying wire, carrying your own weight on boards that flexed and swayed with every step. In gale winds, the catwalks would swing 10 or 15 feet laterally, throwing workers off balance, forcing them to grip the hand ropes and wait for the gusts to pass. In rain, the planks became slick with water, and the spray from below coated everything in a film that made footing treacherous. In winter, ice formed on every surface. The wires became glass smooth. The planks became skating rinks suspended in mid-air. And still the work continued, because winter was often the best time for spinning. Cold, dry air was easier to work in than summer humidity, which could affect the wire's properties. The Niagara Falls Suspension Bridge opened in 1855. It was the first railroad suspension bridge in the world. A 23-ton locomotive crossed that span, suspended from wire cables, and the bridge held. The scientific establishment, which had predicted disaster, fell silent. But Roebling was already thinking bigger. The Cincinnati-Covington Bridge, begun in 1856, would span the Ohio River at a point where the water was 1,000 feet wide. The towers would rise over 200 feet above the water. The main cables would each contain more than 5,000 wires, and the techniques developed at Niagara would be refined into something approaching industrial process. The Ohio River presented different challenges than Niagara Gorge. The water was calmer, but the river was wider. The bedrock was deeper, requiring foundations that extended far below the waterline. And the city of Cincinnati, watching the towers rise on the Kentucky shore, was consumed by the approaching Civil War. So construction halted in 1861 when Confederate sympathizers threatened to destroy the work in progress. For 5 years, the towers stood incomplete, monuments to interrupted ambition. Workers scattered to the armies. Roebling himself traveled to Washington, offering his engineering expertise to the Union cause. When construction resumed in 1866, the wire spinning crews included veterans of both sides. Men who had tried to kill each other 2 years earlier now rode the same baskets across the Ohio, spinning wire into cables that would connect north and south. Think about that for a moment. The physical intimacy of this work. You are in a basket with another man, your lives depending on each other's skill and attention. One mistake, one moment of distraction, and you both fall. In whatever hatreds the war created had to be set aside 300 feet above the water because survival demanded cooperation. The Cincinnati-Covington Bridge, later renamed the John A. Roebling Suspension Bridge, opened in December 1866. It was the longest suspension bridge in the world at that moment, a distinction it would hold until Roebling's next project made it obsolete. The Brooklyn Bridge. If Niagara proved that suspension bridges could carry railroads, and Cincinnati proved they could span great rivers, Brooklyn would prove they could redefine cities. The East River Crossing would connect Manhattan to Brooklyn, the first and third largest cities in America, creating a metropolitan area of unprecedented scale. Roebling's design called for towers 276 feet tall, the highest structures in the Western Hemisphere when completed. The main span would stretch 1,595 feet, with approaches that brought the total length to over a mile. The cables would be nearly 16 inches in diameter, containing more than 21,000 miles of wire each. The scale was staggering, but Roebling was confident. He had proven the principles at Niagara and Cincinnati. The Brooklyn Bridge would be those bridges, perfected and enlarged. He never saw it built. In June 1869, John Roebling was standing on a ferry slip at the edge of the East River, surveying the site where the Brooklyn Tower would rise. He was 63 years old, at the height of his fame and powers. His notebooks were filled with calculations for the Great Bridge. A ferry approaching the slip misjudged its speed. The boat crushed Roebling's foot against the pilings. Doctors amputated his toes, but infection set in. Tetanus, lockjaw. For 3 weeks, Roebling lay in agony as the poison destroyed his nervous system. He died on July 22, 1869, leaving his son Washington to complete the bridge that would become his monument. Washington Roebling was 32 years old when his father died. He had worked beside John on both the Cincinnati and Niagara bridges. He had ridden the spinning baskets himself, walked the catwalks, handled the wire. He knew the work intimately, but he also knew that the Brooklyn Bridge would demand things no previous bridge had demanded. The towers at Brooklyn would require foundations sunk deep into the riverbed, below the water, below the mud, down to solid bedrock. This meant caissons. Enormous wooden boxes open at the bottom, pumped full of compressed air to keep the water out while workers dug beneath them. The caisson work was the most dangerous labor in American industrial history to that point. Men climbed down iron tubes into chambers pressurized to 3 times normal atmospheric pressure. They worked in air so thick it felt like swimming. They dug through sand and gravel and decomposed organic matter, filling buckets that were hoisted to the surface through airlocks. And when they ascended too quickly, they developed caisson disease. The bends, nitrogen bubbles forming in the blood and tissues as pressure dropped. Men came up from the caissons and collapsed in seizures. Some died within hours. Some were paralyzed for life. Washington Roebling spent so much time in the caissons, supervising the work, that he permanently damaged his own health. By 1872, he was largely bedridden, unable to visit the construction site. For the next 11 years, he directed the bridge from his apartment window in Brooklyn Heights, watching through a telescope, communicating through his wife, Emily, who became the bridge's day-to-day supervisor in all but name. But the wire spinning continued, and the crews who performed it were now working at heights no human beings had ever worked before. The Brooklyn Bridge catwalks hung 270 feet above the East River, not above rapids or gorges, but above the busiest waterway in America, crowded with ships and ferries, their smokestacks sometimes passing close enough to touch. The catwalk swayed in every wind. Ships' horns blasted from below. Seagulls screamed around the workers' heads. The sensory assault was relentless. Below, the river stank of fish and sewage and the coal smoke from passing vessels. The wind carried salt spray that dried on your skin and left white crusts on your clothing. In summer, the sun reflected off the water and baked the catwalks until the planks were too hot to touch with bare hands. In winter, ice formed on the cables overnight and had to be chipped away before work could begin. Your hands told you everything. After a few weeks on the cables, your palms developed calluses hard as leather. You could feel the difference between properly seated wire and wire that had crossed or kinked. You could sense when the cable was reaching its design tension by the vibration that traveled through your tools. When experienced spinners claimed they could detect a single broken wire in a bundle of hundreds just by the way the strand felt under their fingers. And still, they walked. Still, they spun. Still, they rode the baskets back and forth, laying wire into cables that grew slowly toward completion. The Brooklyn Bridge required a new innovation in wire spinning. At Niagara and Cincinnati, individual wires had been spun and then bundled into cables. At Brooklyn, the number of wires was so large that the bundling process became impractical. Instead, Roebling developed a system of spinning wire into preformed strands, each strand containing a specific number of wires, which were then combined into the final cable. This sounds like a technical detail, but it changed everything about the labor. Instead of handling individual wires, spinners now worked with strands that were heavier, stiffer, and required more force to position correctly. The physical demands intensified. The margin for error shrank. The contractor who supplied wire for the Brooklyn Bridge was a man named J. Lloyd Hay. In 1878, inspectors discovered that Hay had been systematically substituting inferior wire for the premium product his contract specified. He had hidden the substandard wire beneath coils of good wire, knowing that only the top layers would be tested. By the time the fraud was discovered, some of the bad wire was already spun into the cables. Removing it would have required destroying months of work and spending hundreds of thousands of dollars. Washington Roebling made a calculation. He had designed the cables with a safety factor of 6, so meaning they could bear 6 times the maximum expected load. Even with Hay-Gedabia's inferior wire, the cables retained a safety factor of between 4 and 5. The bridge would be safe. He let the bad wire remain in the cables, added additional good wire to compensate, and fired Hay. But imagine being one of the workers who discovered that the wire you had been spinning, that you had risked your life to position correctly 300 feet above the river, was defective. That your employer had cheated not just the bridge, but you. The Brooklyn Bridge opened on May 24, 1883, 14 years after John Roebling's death. Over 150,000 people crossed it on the first day. President Chester Arthur walked from Manhattan to Brooklyn and back. Emily Roebling rode across in a carriage, a live rooster in her lap as a symbol of victory. The newspapers called it the eighth wonder of the world. They praised John Roebling's genius. They praised Washington Roebling's perseverance. They mentioned Emily Roebling's contributions, a remarkable acknowledgement for a woman in that era. They did not name the wire spinners. They did not name the men who had died in the caissons. They did not name the workers who had walked the catwalks in gale winds, who had fallen from heights no human beings had ever worked at before, whose bodies had been carried from the water or scraped from the rocks. At least 27 men died building the Brooklyn Bridge. That is the official count. The actual number was almost certainly higher. Workers who were injured on site and died later in their homes were not always recorded as bridge fatalities. And workers who developed chronic conditions from caisson exposure and died years later were never connected to the construction. The bridge was built on a foundation of anonymous suffering. This is the cost of progress, not in dollars or materials, but in human lives given to projects that would outlast them by centuries. The Brooklyn Bridge still stands. It carries cars and pedestrians every day. Tourists photograph it from the waterfront. Couples walk across it at sunset. And somewhere beneath its cables, embedded in its wire, is the labor of men whose names we will never know. After Brooklyn, the suspension bridge became standard American technology. The technique spread across the country. The Williamsburg Bridge, the Manhattan Bridge, the George Washington Bridge, the Golden Gate, each one larger than the last, on each one incorporating lessons learned from the bridges before. The wire spinning process was gradually mechanized. Electric motors replaced hand winches. Traveling wheels became traveling sheaves, moving faster and carrying more wire per trip. Safety nets were strung beneath the catwalks to catch falling workers. But the fundamental reality remained unchanged. Human beings had to climb to heights where human beings were not meant to be. Human beings had to handle materials under conditions that did not forgive error. Human beings had to trust their lives to calculations made by men they would never meet, trusting that the engineers had gotten the math right, that the contractors had supplied honest materials, that the weather would hold long enough to finish the day's work. The physics of cable failure is terrifying in its simplicity. A single wire in a suspension bridge cable does not carry a proportional share of the total load. Because the wires are helically wound, some wires bear more stress than others depending on their position in the bundle. When one wire breaks, the stress it was carrying does not disappear. It transfers to adjacent wires, increasing their load. This is called stress redistribution. And if those adjacent wires are already near their limit, the additional stress can cause them to fail as well, which transfers more stress to the next wires, which can fail in turn. A single broken wire can cascade into a chain reaction that unzips an entire cable in seconds. This is why John Roebling insisted on such high safety factors. This is why Washington Roebling was willing to let some inferior wire remain in the Brooklyn Bridge cables rather than risk weakening the structure by trying to remove it. The consequences of cable failure were not gradual degradation. They were catastrophic, instantaneous collapse. Every wire spinner who rode those baskets across the void understood this, even if they could not articulate the physics. They knew that the wire in their hands would someday bear loads that would kill thousands of people if the wire failed. They knew that their work mattered in ways that most work does not matter. They knew that a moment's inattention, a single wire crossed or kinked or positioned incorrectly, could become a defect that would propagate through the cable for decades before finally failing. This is a kind of knowledge that changes a person. Reese, you cannot do work like this without being altered by it. You cannot stand 300 feet above a river, holding wire that will support a city's traffic for the next century, without feeling the weight of that responsibility. You cannot watch another man fall and then climb back onto the catwalk the next morning without understanding something about human courage and human mortality that most people never learn. The wire spinners of the 19th century were not engineers. They were not scientists. Most of them had little formal education. They were farmers and laborers and immigrants. men who needed work and were willing to accept risk in exchange for wages. But they were also practitioners of an extraordinary craft, a skill that required physical courage, manual dexterity, and a kind of practical intelligence that no classroom could teach. They developed their own terminology, their own techniques, their own superstitions. They could feel when a wire was seated correctly by the tension in their hands. They could hear when the cable was approaching its design shape by the sound it made under stress. They could smell when rain was coming by changes in the air that gave them minutes to secure their work before the weather turned. This knowledge died with them. It was never written down. It was never taught in schools. It was passed from experienced spinners to newcomers through direct instruction on the catwalks, in the baskets, in the moments between gusts of wind when speech was possible. We have John Roebling's notebooks. We have Washington Roebling's reports to the Bridge Company. We have contemporary newspaper accounts and official records, but we have almost nothing from the workers themselves. They left no diaries. They wrote no memoirs. They were too busy working, too tired after work, too focused on survival to document their experience for posterity. And so we must imagine them. We must reconstruct their lives from fragments. We must stand at the base of the Brooklyn Bridge and look up at those cables, at the towers rising above us, and try to feel what it felt like to be 300 feet higher, balanced on a plank, holding wire, with nothing between you and death but your own skill and attention. Imagine the moment before you step onto the catwalk for the first time. You have watched other men do it. You have been told it is safe, that the cables are strong, that workers cross every day without incident. But your body does not believe what your mind has been told. Your legs shake. Your hands sweat. Your vision narrows until all you can see is the plank in front of you, the void on either side. You step, the plank flexes, the cables sway. The wind, which seemed gentle at ground level, becomes a living force trying to push you off balance. You take another step, another. You reach the first support post and grip it with desperate strength. You realize you have been holding your breath. Somewhere ahead, an experienced spinner is walking casually, tools in one hand, the other hand barely touching the guide rope. He has made this crossing 1,000 times. He no longer feels the fear that grips you, but he remembers it. Everyone remembers their first crossing. You keep walking. Step by step, the fear recedes. Not because the danger lessens, but because your mind learns to contain it. You learn to move with the sway instead of fighting it. You learn to shift your weight when the wind gusts. You learn to trust the cables, the planks, the system that holds you above the void. By the end of your first day, you have crossed the catwalk dozens of times. By the end of your first week, you barely notice it. By the end of your first month, you are the one walking casually while new workers grip the support posts and tremble. This is adaptation. This is how human beings survive impossible environments. We learn. We adjust. We normalize the abnormal until it becomes routine. But the danger never goes away. The veterans fall as often as the newcomers, sometimes more often because they have stopped being afraid. They take risks that the newcomers would never take. They trust their experience when they should trust the physics. They forget that the wind does not care how many crossings you have survived. The bridges themselves were monuments to this adaptation. They were built by human beings who had learned to work in environments that should have been impossible. They stood as proof that fear could be overcome, that risk could be managed, that the impossible was merely the not yet achieved. But they were also graveyards. Every suspension bridge of the 19th century contained the bones of its builders, sometimes literally. Workers who fell during construction were not always recovered. The rivers were deep, the currents strong. Some bodies were carried downstream and never found. Some were buried in the foundations, entombed in concrete and stone. John Roebling understood this cost. In his letters and notebooks, he wrote about the workers who died on his projects with something approaching guilt. He designed safer systems, developed better equipment, instituted procedures intended to reduce accidents. But he also knew that the work could not be made safe. It could only be made less dangerous. The wire rope itself was Roebling's greatest contribution to worker safety. even though most people remember it as an engineering innovation. Before wire rope, suspension bridges used iron chains or hemp cables. Both were prone to sudden failure without warning. Wire rope, by contrast, degraded gradually. Individual wires would break, but the cable would continue to function. Workers could inspect the cables and identify developing problems before they became catastrophic. This is the strange mathematics of safety in dangerous work. You cannot eliminate risk. You can only shift it, redistribute it, make it visible instead of invisible. John Roebling's wire rope did not make suspension bridges safe. It made them predictably dangerous, which, in the logic of engineering, amounts to the same thing. The Trenton Wire Rope Factory that Roebling established in 1841 operated for over a century. It produced wire for bridges, for mines, for ships, for elevators. It employed thousands of workers over its lifetime. Men who drew wire through dies, who twisted wire into rope, who wound rope onto spools for shipment across the country. This work was also dangerous, though in different ways. The wire mills were filled with spinning machinery that could catch a sleeve and pull a man into the gears. The drawing rooms were hot, the air thick with lubricant mist. The twisting machines produced noise that permanently damaged workers' hearing. But the factory workers had one advantage over the wire spinners on the bridges. If they fell, they only fell a few feet. If a machine grabbed them, their co-workers might be able to stop it in time. The dangers were immediate and comprehensible, not the abstract terror of heights. The men who worked in the factory and the men who spun the wire at the bridge sites rarely met. They were different workforces, separated by geography and skill, but they were connected by the wire itself, by the long chains of material that began as raw iron ore and ended as cables capable of suspending cities. This is how industrial infrastructure worked in the 19th century. Each step in the process required specialized workers who understood their particular task intimately, but knew little about the larger system. The miners who extracted the ore knew nothing about wire drawing. The drawers knew nothing about wire spinning. The spinners knew nothing about the physics of suspension bridge design. John Roebling was unusual because he understood the entire chain. He had studied metallurgy in Berlin. He had experimented with wire manufacturing techniques. He had designed the spinning systems used on his bridges. He had supervised the spinning operations personally. He held the whole picture in his mind in a way that few other engineers could match. But even Roebling could not control everything. He could not guarantee that the ore miners would extract pure iron. He could not guarantee that the wire drawers would catch every defect. He could not guarantee that the spinners would position every wire correctly. He could not guarantee that a ferry captain would see him standing on the slip. The Brooklyn Bridge stands today because thousands of decisions went right, but it also stands because John Roebling designed an enough margin for error that some decisions could go wrong. The bad wire from Hayes fraud remains in those cables, a permanent record of human dishonesty embedded in a monument to human achievement. We build things. This is what humans do. We build things larger than ourselves, things that will outlast us, things that will serve purposes we cannot imagine. We pour our labor and our lives into these constructions, and then we die, and the constructions remain. Yeah, the men who spun the wires of the Brooklyn Bridge have been dead for over a century. Their children are dead. Their grandchildren are mostly dead. Whatever pride or fear or exhaustion they felt on those catwalks has dissipated into the general human past, indistinguishable from the experiences of a billion other forgotten workers. But the wire remains, the cables remain, the bridge remains. Every day, thousands of people cross the East River on a structure that exists because anonymous men were willing to ride baskets through empty air, trusting their lives to the mathematics of tension and the quality of wire. This is immortality, if immortality exists at all. Not the survival of your name or your memory, but the survival of your work. The wire spinners are gone, but the work they did continues to function, continues to serve, continues to matter. When you walk across a suspension bridge, any suspension bridge, you are walking on wire that someone had to spin. Someone had to position each strand. Someone had to verify each joint. Someone had to trust the system enough to climb back up the next morning and keep working. These bridges are not miracles of engineering, though they are often described that way. They are miracles of labor. They are monuments to the willingness of ordinary human beings to do extraordinary things, to accept risk that most people could not contemplate, to give their effort and sometimes their lives to projects that would benefit people they would never meet. John Roebling saw wire as the solution to an engineering problem, but wire was also the connection between thousands of workers and millions of users. Why a material thread linking those who built to those who crossed. The wire does not care who spun it or who walks on it. The wire simply does what wire does, bearing loads, distributing stress, holding fast against forces that would tear it apart. And this, perhaps, is the final lesson of the wire spinners. The work matters more than the worker. The bridge matters more than the builder. The structures we create will outlast us, and they will serve purposes we cannot predict, and they will be maintained by people who know nothing of the original builders except that they existed. This is not tragedy. This is simply the way of things. We give what we have to give, and then we are gone, and the world continues without us. The wire spinners gave their strength, their skill, their courage, their lives, and in return, they received wages and the satisfaction of work well done. Was it enough? Did they feel cheated by history, forgotten before they were even dead? Or did they understand that their work spoke for them, that every carriage and train and automobile that crossed their bridges was a kind of memorial? We cannot ask them. We can only stand on their bridges and wonder. The Roebling Suspension Bridge in Cincinnati still carries traffic. The Brooklyn Bridge still carries traffic. The techniques John Roebling invented, refined by his son and by the engineers who followed, still define how suspension bridges are built. If you visit these bridges today, you will find plaques and monuments commemorating John Roebling. You will find historical markers describing Washington Roebling's struggle and Emily Roebling's contributions. Tourists photograph the towers. Architecture students sketch the cable patterns. Engineers study the calculations that made these spans possible. But you will find no monument to the wire spinners, no plaque listing their names, no historical marker describing the men who rode baskets through empty air, who walked catwalks in gale winds, who fell and were carried away by currents. They exist only in the aggregate, as numbers in construction reports, as statistics in safety records, as unnamed figures in contemporary illustrations. Perhaps they would not have wanted monuments. Perhaps they understood their role more clearly than we do. They were not building for glory. They were working for wages, feeding their families, surviving day to day. The bridge was incidental to their lives, even as their lives were essential to the bridge. The wire has gotten stronger. The cables have gotten larger. The spans have stretched to lengths that would have seemed impossible to the wire spinners of the 19th century. The Golden Gate Bridge, completed in 1937, hangs from cables over 36 inches in diameter, containing more than 27,000 individual wires each. But someone still had to spin those wires. Someone still had to ride between the towers, positioning strand after strand until the cables reached their design diameter. The technology changed, the safety equipment improved, the wages increased, but the fundamental work remained the same. Human beings, suspended above voids, spinning wire into cables that would hold cities together. This is how America built 2,000-foot suspension bridges using only wire and stone. Not with genius alone, and though genius was required, not with machinery alone, though machinery helped, but with human hands, human eyes, human courage, human labor. The wire spinners. They walked where no one should walk. They worked where no one should work. They trusted calculations they could not verify and materials they did not manufacture. They accepted risks that would paralyze most people. And they built structures that would stand for centuries. Their names are lost. Their faces are lost. Their voices are lost. But the wire remains. The bridges remain. And every time you cross one, you are walking on their work, supported by their labor, held above the void by strands that human hands once positioned in the empty air. Remember them.